Good morning to everyone. Today we are going to see the introduction to digital signal processing. So under this we will be seeing about introduction to DSP, DFT and its properties, fast Fourier transform using DIT and DIF algorithm, and convolutions using overlap add and save method. First of all, what is digital signal processing and what are its benefits? By a signal, if we are in a position to transfer some kinds of information that can be conveyed, displayed or manipulated. Some examples of signals are speech. So we will be encountering speech in telephony, radio and everyday life. Next one is our biomedical signals, that is our heart signals as well as our brain signals. So next is sound and music as produced by the CD player, video and image, radar signals. So usually radar signals are used to determine the range and bearing of distant targets. So next, there are some advantages while we are going for DSP. So first one is guaranteed accuracy. So usually we will be determining accuracy based on the number of bits that we are using in our process. Second one is perfect reproducibility. So from unit to unit, we will be identify the performance which is identical. So usually a digital recording can be copied or reproduced several times with no loss in signal quality. Third one is no drift in performance with temperature and age. Fourth one is uses advance in semiconductor technology to achieve smaller size, low cost, low power consumption, higher operating speed. Fifth one is greater flexibility. So we no need to modify the hardware that we are using in our DSP processor. And finally, superior performance. So here your linear phase response can be achieved as well as the complex adaptive filtering becomes possible. So next, so though there are many advantages of DSP, there are some disadvantages in DSP. So first one is our speed and cost. So usually DSP processor can be expensive, especially when large bandwidth signals are involved. Either ADC or DAC are too expensive or do not have sufficient resolution for wide bandwidth applications. Second one is it is time consuming, plus we need the necessary resources. And third one is finite word length effects. If only a limited number of bits is used due to economical consideration, serious degradation in system performance may occur. So next there are some applications of DSPs. First one is image processing. Next one is instrumentation and control. Third one is speech and audio. Fourth one is military application. Fifth one is telecommunications. Sixth one is biomedical applications. And finally, consumer applications. So next, why we are going for digital signal? So usually, DSP techniques are so powerful that sometimes it is extremely difficult, if it is not possible, for an analog signal to achieve similar performance. For example, a FAR filter with linear phase as well as adaptive filters. So usually, analog signal processing is achieved by using analog components such as resistors, capacitors and inductors. So the tolerance associated with these components, temperature, voltage changes and mechanical vibrations can dramatically affect the effectiveness of these circuits. So next, with DSP, it is easy to change our application, correct our application and update our applications. So usually, DSP will be reducing the noise, chip count, development time and cost. So next, usually high frequency signals cannot be processed digitally because of two reasons. First one is analog to digital converters. So here ADC cannot work fast enough, and second one is the applications can be too complex to be performed in real time. So next, this is the block diagram of our ADC. So this X of t is nothing but our continuous time signal. So usually ADC is used to convert all our analog signals into digital signals. So our input to the system will be an analog signal and the output of the system will be digital signals. So here x of t is nothing but an analog signals. So all our signals will be varying with respect to time t. Whereas in digital signals, it is x of n, where n is nothing but number of samples. So we will be giving a continuous signal x of t to an analog low pass filter. The output of this low pass filter can be fed as input to the sample and hold circuit where the process of sampling happens. So x of t, by undergoing this sampling process, will be converted into x of nt, where capital T is nothing but sampling time period. When we are giving this x of nt as input to this quantizer, what this quantizer will be doing means it will be reducing the error that occurs in this signal x of nt. So at the output of the quantizer, we will be getting an digital signal x of n, which is given as input to our DSP processor. So this is an example of analog to digital converter. So you initially will be giving this analog sine signals. So based on this sine signal, it will be converted into a clock. Based on the clock signals, it will be converting into digitalized signals. So next, digital to analog converter. So after converting our analog signals to digital signals, in all our day-to-day components, we will be giving analog signals as input and analog signals as output. So the process inside those things will be in the form of digital. So after acquiring our digital signal, it is our responsibility to convert all our digital signals into analog signal once again. Therefore, from the DSP processor, the output of the DSP processor will be digital. So this digital signal will be given to your DAC, that is nothing but digital to analog converter. So after that, here too a sampling process will be going on. After the sampling process, we will be giving that sampled signals to our low pass filter. So at last, the output of the low pass filter will be continuous time signal. So next, why we are processing signals? There are 6 main criteria for us to process a signal. So first one is our extraction of information. Second one is transform the signal. Third one is compress data. Fourth one is generate feedback control signal. Fifth one is extraction of signal in noise. And at last is store the signals in digital format for analysis. So next, this is the block diagram of our digital telephone communication system. So initially, we'll be giving our voice signal as analog signal to the ADC block. This ADC block will be undergoing the analysis process. After analysis process, it will be going to quantization process. So the output of the quantization will be encoded, and those encoded bit patterns will be given as encrypted messages, and at last we'll be undergoing some modulation technique. So this, after modulation technique, those analog waveforms will be fed as input to the telephone channel. So once again, in the receiving side, we will be undergoing a demodulation process followed by unscramble. Then we will be decoding our bit streams, after that synthesis, and finally digital to analog signals. So this is our typical architecture of a DSP system. So first we will be giving analog signal, and at last we will be getting a digital signals. So we'll be using a sensor followed by analog signal conditioning. So this analog output of this analog signal conditioning will be given as input to our analog to digital converter. So next it will be undergoing digital signal conditioning, after that DSP processor, and finally digital to analog converter. So at last, why do we need a DSP processor? So usually we are in need of a DSP processor in order to save our cost, smaller size, low power consumptions, and processing of many high frequency signals in real time. And second thing is, use a general purpose processor when the followings are required. So we can use our GPP processor when we are in need of large memory and advanced operating systems. Thank you.